We
Good
have
evening, Professor.
Good evening. Good evening.
How
Miss
are you
Moran,
doing?
I'm good.
Yes.
I'm good. Did you hit similar exercise? Because with the thing you were telling me about.
Um, so no, what happened was is I went to the chapter review and it wouldn't um it said that it told me in the beginning that you would not be able to make any changes because everything was already submitted or something, that you could not make any changes. So
Hmm.
I'm thinking because I took the chapter test before I did the review, I'm thinking that maybe it's not going to allow me to do that.
No, because they're not connected in any way. So what you do, taking a test and all this stuff, that has nothing to do with each other. So it's got to be something else going on there. Might have to
Mm.
meet one day and let you share your screen or something like that, so I can see what you're doing, what you're
I
clicking on
mean,
and stuff like that.
I can go to it.
Mhm.
I know we have class,
Yeah.
but
So okay, so we can do it after class and make sure you're good before we leave. Yeah, make sure you're straight.
okay, cause I don't know why it's saying that.
Hmm. We'll figure it out.
Okay.
All right. So good evening, everyone. Hope all is well. Hope everybody's doing all right. Hope you had a great week last week and ready to get this one rolling. So last class we finished off 5-3, so we should be picking up at 5-4. Any general questions or concerns before we get rolling? Everybody good? Okay. All right. Mm. Checking on stuff. So yeah, we already did this. 5-4. There we go. All right. So if I'm not mistaken, this is a lot of statements. Yeah, just going in. Okay, cool. So 5-4, just finding empirical and simulated probabilities. So empirical probabilities are probabilities based on carrying out real life random actions and observing the relative frequency that an event of interest happens. Next statement, finding empirical probabilities can be slow and laborious. And for this reason, it is often useful to perform a simulation that can be carried out rapidly.
You said, and for this reason?
Let me see. Yep, and for this reason, it is often useful to perform a simulation that can be
Thank you.
carried out rapidly. Yep, no problem, no problem. Is everybody done with the first one? Then the next statement, simulations can also be helpful when a situation is too complex to find a theoretical probability. Let me know if I'm going too far. See if I can get this example in here. All right, so first example of the section, we wish to know the probability of getting exactly 2 heads if we flip a coin 3 times. To find an empirical probability of this event, we flipped a real coin 3 times and noted whether or not there were exactly 2 heads. We repeated this for 5 trials, and then they give the results. I'll give you guys a chance to write this down, then I'll scroll up for the results. All right, scrolling up. So here are the outcomes. Yep, still unmuted. Here are the outcomes. And I remember there were 5 trials, and you were to flip the coin 3 times. Want to know for these results, when did we get 2 heads and just 1 tail? So you notice the first time, the second time, and the third time got just the 2 heads. Now scroll up. So the question here is, what's the empirical probability of getting exactly 2 heads and 3 flips based on this data?
Two fifths.
So right down with the purple. And so when you look at what we have here, we have 5 different trials ran. Out of those 5, 3, was what we wanted, had the outcome of what we wanted. So in the green, that would be answer 3 out of 5 times we got the 2 heads. So 3 over 5 is 0.60, that's 60%.
I think that's problem number.
Questions on what we did there, make sure we're okay. Can I scroll up? So questions that should or may come up when you're looking at this. Why is this important? Why can't we rely? How'd you get 60? Well, you divide 3 by 5. So that's just 3 divided by 5. That 3 over 5 is just 3 divided by 5, and that gives you 0.60. They move the decimal 2 places to the right to convert it to 60%. Yeah. So 5, when you divide 5 into 3, that gives you 0.6. I think that's what you were asking. If not, let me know. All right. So why can't we rely on this? Probability. Why can't 5 trials be enough to determine a dependable probability? All right, somebody says something. Okay, cool. Yep, all right, good. All right. Can I scroll up? Hold on 1 second. Let me check out something real quick. Okay. All right. So when you're looking at this, this is important to give you an estimate, but it's not reliable because that's a very small sample size on what could happen. If you do that a couple more times, the percentage could go from 60 to 10%, just depending on what's going on. So we're going to need more trials to be ran, and that's where the law of large numbers come into place. So the law of large numbers is just a theorem that tells us that if our simulation is designed correctly, then the more trials we do, the closer we can expect our empirical probability to come to the true probability. So you're talking about running a simulation 100 times instead of just 5 times, or 500 times instead of just the 5 times. And the more you do it, the closer you get to the real probability or the true probability. So that's what the law of large numbers state.
Hold on. What was that word right after A?
Theorem. Talking about right here?
Yeah.
Yep, theorem.
Okay, thank you.
Not a problem. All right, can I scroll up? No, I'll leave that. All right, so as we approach infinitely many trials, the true probability and the empirical probability approach the same value.
What does that say in parentheses?
Theoretical.
My office hours are on Friday at 9 a.m. for your penmanship, okay?
Too funny. All right, can we scroll up from the law of large numbers? And so this next example is just emphasizing what we're talking about when you're saying that you need, infinitely many flips versus just doing it 10 times or 100 times. So we'll see the difference in what we get out. All right. So example to try to put an application to what we're talking about here. Let's say if we're talking about flipping a coin and landing tails. So landing tails is our event, flipping the coin is the experiment. So if I flip a coin 10 times, the result could be 7 tails and 3 heads, which would make the empirical probability 7 out of 10, which is a 70% chance of landing tails. So if I just go off of flipping a coin 10 times, if I were to land tails 7 times and heads 3 times, that means that if I go off of that, that means I have a 70% chance of landing tails. But we know from doing the probability calculation, the true probability is a half, 50% chance. Everybody done with the black? So if the coin is flipped more times, then the probability will come closer and closer to that 50%. And so that's what we're talking about, the law of large numbers. The more and more you do or perform an experiment, the more and more you come closer to the true probability, that theoretical probability. So simulations are normally done by some type of program or application or technology. So what if my simulation does not give the theoretical value I expect? Then there are two possible explanations. So the first one is that your theoretical value could be incorrect. Second is that your empirical probability is just varying. And so if you just do more trials, it will probably get closer to your theoretical
Excuse me,
value.
can you scroll back where the green is, please?
How far you need to go up?
Says 1/2, 50% right there.
Okay.
Thank you.
Mhm. All right. That's that last statement in red. All right. Anyone still copying? Can I go to the next sheet?
Question number 2, in the red, it says it's just, what is that?
Varying.
Varying, okay.
Mhm.
Okay.
All right. Anybody else before we go to the next thing? Everybody good? So that's it for chapter 5. It's 5.1 through 5.4. Try those things out, see if you have any questions, and we'll address them. Somebody was saying something?
Pardon me.
Oh, okay, okay. All right, so let's look at 6.1. Okay, yeah. So there are only 2 sections in chapter 6. So let's at least do 6.1 today. We'll see how short 6.2 is, but 6.1 probability distributions are models of random experiments. All right, so the probability model is a description of how a statistician, statistician, All right, thanks. Data are produced. All right, I need to magnify it a little bit. So probability distribution, sometimes called probability distribution function. That's your PDF, sometimes called PDF for short. It's a tool that helps us by keeping track of the outcomes of a random experiment and its probabilities. Well, I'll give you a chance to write that before I scroll up. All right. So it tells us all possible outcomes and also tells us the probability of each outcome. Of course, let me know if I go too far up on the black. All right, so discrete outcomes or variables are numerical values you can list or count. Continuous outcomes or variables cannot be listed or counted because they occur over a range. So measured or weighted things would be an example of that. So, if I'm not mistaken, I have some. Yep, we'll do some more examples anyway. So, but key to that would be measured or weighted. Are you measuring something or weighing something? That would be considered continuous. All right, scrolling up. Of course, as always, let me know if I go too far. So this first example, or the first exercise, we're trying to decide between something being discrete versus being continuous. I already kind of got the answers up there. So instead of me erasing it, we're just talking about why it is what it is. So it's late in the game, y'all. It's late in the game. So the weight of a sandwich at the deli. So remember, I just mentioned over here in the green, if something is measured or weighted, it's considered continuous versus being discrete. So continuous, when you talk about measured and weighted, the reason why it's not something that you just consider that you could count is because if your scale is more accurate than mine, your answer will be right, but that doesn't make my answer wrong. So in other words, let's say if something weighs 5 grams, but yours go to the 10th place, then that's you can get 5.1 grams. But if the next person have a scale and theirs go to the 100th place, they can have 5.12. So you have 5, 5, 1, and 5, 1, 2. All three of them still correct. It's just that your scale may be more accurate than mine. So that's why it's considered continuous. All of those answers are the same, are correct, even though certain ones are more accurate than the others, or more precise. I won't say more accurate, more precise. So if you're going to weigh something or scale something or measure something, then that's considered continuous. When you can actually put a number on it and like there's no other number but that answer, then that's when it's considered discrete. So the number of people in the car passing by you. So there's either 4 people in the car or it's not. So it's either 4 people or 3 people. At least have to be one person, right? If the car's passing beside you. So whatever it is, there's no such thing as 1.2 person or 1.3 of a person. So, if it's something you can count, it's not, there's no other distinction. It's either 3 or it's not, then that's when it's considered discrete. I still holding on to that purple. The blood level of a driver pulled over by the police in a sobriety check. Once again, this is something that's measured. I think it's a gun that you have to blow into. I've never done it before, so.
Mhm. Mhm.
You know, whatever it is, look, whatever it is y'all be doing, I'm just playing. But you know, somebody's gun is more accurate than the next man, whatever. When anything that you have to measure or beat or weight or scale, that's considered continuous. All right. And then that last one, the number of eggs laid by a chicken, that's discrete because you can count how many eggs and there's no discrepancy in that, no
Oh, okay.
deviation from it. There's 4 eggs, there's 5 eggs, or there's, you know, whatever, how many eggs there are. No such thing as 6.1 egg, 6.2 egg, something like that.
Depends on if you're talking about eggs that have extra yolks in them or not.
What you mean?
You've never had an egg with like a double yolk in it?
Oh, come on. Now, I'm about to get confused.
I'm
She
sorry,
going
I
too
meant
deep.
it as a joke. I don't mean it for real though, but there is
No,
like
I know.
double yolks.
I'm just making light. I'm just being funny.
Yeah. Somebody always got to go deep. Got to go too deep.
I mean, I did take philosophy already, so
She isn't wrong though.
Yeah, well, that's why I said I couldn't say she was wrong. I guess it depends on what your definition of egg is. Like, you know, I don't know. You know, if you're saying the shell, I don't know, you counting yolks, I don't know. Still see writing, so we're okay.
It's raining hard.
Let me see, are we ready to go? Like most everybody's done writing. All right, let's go to the next thing. Of course, if you're still writing, let me know. All right, so here we said give a table that shows the probability distribution for the amount of money you will win. Draw a graph of this probability distribution function. So then in purple, they give us the actual example that we're going to lean on. We're done with the discrete. All right. So we got roll a fair 6-sided die. You will win $4 if you roll a 5 or 6. You will lose $5 if you roll a 1. For any other outcome, you will win or lose nothing. All right. So we're going to create a table that's going to show how much money or how the money will be dispersed according to what we roll. So we got a fair 6-sided die. You will win $4 if you roll a 5 or 6. You will lose $5 if you roll a 1. And then for any other outcome, you will get nothing. Won't lose anything either, but you won't win anything.
So on this problem versus the problem in 5.2, I think, or 5.3, the difference is we're going to have to do a graph.
Right. So in this case, we're looking at, they're not actually asking us, well, let me say it like this. They want a table of all of the situations that occur in here. We have 3 main situations that are happening here. You winning $4, you winning $5. You winning $4, you lose $5, or you don't get anything, or nothing happens. So those are your 3 outcomes. So we're going to create a probability distribution.
Glad I don't gamble.
Well, you know, when it comes to gambling, it's a higher percentage of losing than it is winning, you know. So You know, they're trying to get that money. If I actually showed you the probability of you winning the lottery, it would, yeah, it would, you would know why it gets so high, you know. Matter of fact, so like, let me see, what's the good one? If you choose, how many did I do that for? It's like they give you 1 through 30. Let's say they give you 30 numbers to choose from, and you can choose 6 out of the 30. That would be the winning combination. But that winning combination is only one ticket. Like, you would actually have to purchase 1 million tickets in order to get it past like 4%, like 4% chance of winning. And so, like, if you paid $1 per ticket, that's $1 million. Like, you could have saved. You know what I mean? And then, of course, the numbers that they select is way over 30. You know what I mean? So, yeah, that the chance.
And they keep adding more numbers.
Yeah. And that's the crazy thing about it. And so that decreases your chances, you know, that much more. So yeah, actually winning is really just, you know, just a shot in the dark. So really the best way, not trying to tell you the best way to gamble, but the best way to actually purchase tickets, you should just keep running the same numbers. Like when you keep switching numbers, that
That's how
decreases.
you do it.
It actually decreases.
Exactly how you win.
You just keep running the same numbers. Yeah. So like I was just mentioning to your classmate, hold on, you will lose $5 if you roll 11. Hold on, that's not what to say. We'll win $4. You will roll 5 or 6. You will lose $5. You roll a 1. Why do I got win $5 or lose $5? Hold on, don't copy that second statement.
Okay.
Just want to make sure. I'm looking at this right here. Roll a fair 6 out of die. You will win $4 if you roll a 5 or 6. You will lose $5 if you roll a 1. That should just be lose $5 or roll a 1. Yeah, you lose any. Yeah, so that should just be lose $5. All right, so those are your 3 outcomes. All right, anybody still holding on to that dark purple?
I'm still right there.
Okay, not a problem.
Scroll up just one more line. Sorry.
Oh no, you're fine. You're fine.
I had to run and grab the dinner out of the oven, so
Oh,
I missed
no.
a few seconds.
Oh man, no, now you messed up because you telling me you got dinner and you're not sharing with anybody. That's where you messed up. You were wrong with telling me to scroll up. Yeah, but it's fine. It's fine.
Okay, I'm done with that part now. Thank you so much.
Yeah, not a problem. Not a problem. Yeah, I missed the ball. That should be lose. People just be letting me write anything on these notes. All right, so these occur when if you roll a 5 or 6, you win $4. You roll 2, 3, or 4, you win nothing, and then you roll a 1, you lose $5. So you know there are 2 shots out of the 6, 5 and 6. That's how we got 2 over 6 here. 2, 3, 4 is 3 out of 6. And then to lose, that's just 1 out of 6. All right, any questions on what I've written so far? Make sure we're okay. We're holding on to red. All right, let me see if I can get this whole chart in here. All right, so if you were to convert these to decimals, I didn't write that up there. But if you're talking about a decimal, that's 0.3 repeated. This is 0.5. And this is, just want to make sure 1 divided by 6. Yep. 0.16 repeated. So we're showing that our result, you know, this one is reference to losing $5. That's why it's a -5 right here. And we brought it all the way up to almost 0.2 because it's 0.16 repeated as a decimal. $0 is 0.5. So that's why this went up here. And then 0.3 repeated. It looked like I went a little higher. Well, yeah, it is a little over 0.3. I guess you would, yeah, that's fine. So this is 0.3 repeated. It's not exactly 0.3, it was a little over 0.3. And that's getting $4. So dollars are down here. All right, any questions on what we did so far?
That says 0.16.
0.6. You talking about, where are you? Right
Yeah,
here?
that right there.
Oh, that's 0.16 with the bar over the 6. The 6 is being repeated.
Okay.
Mhm. All right, how we good looking? Can I scroll up? Guess if I screwed up a little bit, you saw winning dollars right there, right? Yep. All right, so that's it for 6-1. That's how they ended it. So make sure we're good with 6-1. We'll go ahead and knock out 6-2 and call it a night unless somebody want to do some more. We can jump into chapter 7. I know y'all can't wait to get to chapter 7 and all that good stuff like that.
I would much rather not.
I was getting ready to say, like, the sarcasm.
I didn't know if anybody was here listening. I was just talking, you know.
Oh, no, we're listening.
We're listening.
Everybody good with this? So I can scroll up. Everybody good?
Yeah.
All right, all right. So 6.2, the normal model. We talked a little bit about this already, but we're getting to the point where we're about to actually start using it in applications. So we talk about normal model, which is most widely used probability model for continuous numerical values. The curve used to visualize this is called the normal curve or normal distribution. Also called the bell-shaped curve. That's this right here. Your mean is in the middle. So we'll be using Greek letter mu for our probability and lowercase sigma for the standard deviation of the probability. Seen those before. All right, scrolling up a little. So normal distributions, I think I already mentioned symmetric about the mean. Our mean is going to be in the middle. It is unimodal and bell-shaped. If you see the notation with that capital N parentheses and two numbers, that first number is your mean, second number is your standard deviation. So we're talking about right here. So if you see a capital N parentheses, one number comma the next number, first number is that mean, second number is your standard deviation.
Question.
Mm-hmm.
Will we still be able to use the calculation? The calculator that you?
Well, in this case, at this point, they believe you're pros at finding
Mhm.
standard deviation, so they're going to be giving it to you. Now, yeah, like finding the standard deviation is like, they y'all good with that. Now we don't give you the standard deviation. We're gonna do other things with it. Yeah.
Okay. Thanks.
Mm-hmm. Good question. Good question. All right. Well, here's an example of that notation. Capital N, 75, 3 just means that your mean is 75, standard deviation is 3.
All right. This is that distribution?
We are right here.
Yeah.
Yeah, normal distribution.
Okay, just making sure so I knew.
Yeah, no, you fine. You fine. Not a problem. All right, so here in 0, 1 is the standard normal model with mean of 0, standard deviation of 1. So when we go to our z-score chart, you're gonna see, you know, we have that, what's going to be in the middle is our mean, and that once you convert it to that standard, your mean is going to be 0. So I believe Matt asked you a question like that, you know, for the standard normal, you know, what is your mean standard deviation? So 0 and 1 would be that. Give you a chance to finish writing. All right, scrolling up. All right, so z-scores, just mentioned that we're going to use to convert to a standard way of looking at data. So z-scores converts the data values into how many standard deviations they are away from the mean. All right. So here goes the formula. Believe this is our second time dealing with z-scores, but now we're getting into the application of it. I think before all we did was calculate it and talked about a little bit of how we apply it, but so your z-score is the data value minus the mean divided by the standard deviation. But if you put it into symbols, x minus mu divided by sigma, they both mean the same thing. You just need to remember data value minus the mean divided by standard deviation.
Can you scroll up just a little bit, back up a little bit? Right there, right there. If I could just get that last part right there.
Okay.
So you're supposed to let this boil for 30 seconds. I'm just gonna put it on medium. And now I'm just gonna set a time for 30 seconds so it can boil. Boil, bro, boil.
Get out the camera. Call Erica and tell her I'm in math class. I'll call her right after I get up.
You muted.
Oh, sorry.
No worries.
I was trying to catch it. I couldn't get to the button. All right. Are we good with that? That first statement up top? We good? Okay, let's get back to this part. All right. I'll go up too far, let me know. So always round to range z-scores to 2 decimal places. That's going to come into play when we go to our z-score chart. After your z-score is found, you go to the z-score chart to get the probability. That's what I just finished mentioning. And that should be on pages A2 and A3 in your appendix. So let me confirm that, make sure nothing has changed. Yep, A2. Yep, we good. A2, A3. Oh, where's my pen? Hypothesis. All right, can we scroll up, scroll up? So a newborn seal or small newborn seal pups have a lower chance of survival. Suppose the length of a newborn seal follows normal distribution with mean 29.5 inches and standard deviation of 1.2 inches. What is the probability that a newborn selected at random is? Is anybody still holding on to blue? Shorter than 28.0 inches. All right, so let's see what this means for us and what we can do with it. So first thing we want to do is convert that to a z-score. So we pick out, whenever dealing with a word problem, it's always best to pick out or extract all of the information given. So they give us the mean, which is 29.5, give us the standard deviation, which is 1.2, and then the data value that's in question. We want to know the probability of being shorter than 28.0. So 28.0 is our data value, our X. So once you have
You
those
said-
three,
You said X was what?
28.0, right here.
Mhm.
Yep. So anything that, whatever it is that we're talking about being shorter than, taller than, less than, above, you know, whatever that data value in question is that we're doing a comparison to, that is our X value. Then you put it in your z-score formula, X minus mu over sigma 28 minus 29.5 over 1.2, and that gives us negative 1.25. All right. So now we're going to talk about this chart, and I'm going to go to it, but I'm going to show you how you're going to read it. You scroll up past the black. Anybody else still up there? All right. So we got the value of negative 1.25. So when we go to our z-score chart on this, and I'm gonna scroll back up. I just want to show you this. On this left column is negative 3.4 to positive 3.4. And then on the top row is 0.00 to 0.09. All right. So how we'll read this is that if we look at this 1.25, we're going to take the negative 1.2, look for that over here, and the 5 is going to be up here. And where they meet at is the value we're going to pull from the chart. All right. So if I have, let's say if I had 2.65, I want to do 65, 2.68. I would look for 2.6 over here, and the 8 would be up here. All right. And where they meet at is the value that I'm going to choose from the chart or pull from the chart. All right. So can I go to the chart? Anybody still copying?
Can you explain that one more time?
I'm about to show you in the chart.
Okay.
Mm-hmm. If I can get back to it. All right. Well, I want to let me go back to Zoom. All right. There we go. Let's do that. All right. So this is what your chart looks like.
How are we supposed to see that?
Look, you know what? You about to be fired. You let me teach. I'm gonna get this thing magnified in a second.
I'm gonna need like 5 hours to copy this.
I'm with you. I'm with you, EJ.
Please do not copy this chart. Please do not copy this chart. I will send you a copy.
I know it'll be beneficial.
Yeah,
That's just too many numbers.
Yeah, I'll try to shoot that to you this evening. So we're gonna look for, notice our value is negative 1.25. So we're gonna look for the negative 1.25. I mean the negative 1.2 over here. All right, so negative 1.2 is right there. And the 5 is right here. Is everybody okay? And where they meet at is the value we're gonna pull from the chart. Is that okay, Ms. Pinson?
Got it.
You got my son over here like, whoa. He's taking pictures of the screen.
Oh, okay. Well, look, if you ever want to come to office hours, you know how to find me. All right, I see the thumbs up. Sounds good.
It's like, Mom, what are you learning? I'm like, nothing.
All right. Everybody okay so far with how we get our value? So let's say if I have, let's go back to the 2.68. So if I had 2.68, now notice all of these are negative. So I have to go to the positive side where 2.6 is. So 2.6 is right here. 8 is up here. And so where they meet.
0.9.
Yep, 9963. Yep.
Okay.
So is this gonna be like a chart that's given to us, or is there something we have to calculate?
Yeah. So remember I said in one of the statements, I said it's in A2, A3 in your appendix. So it's already accessible to you through your appendix. I'm going to just send you a copy just cause. I mean, but yeah, if you go to the back of the book, as a matter of fact, I think I have it pulled up as far as the book. Yeah, I did. Because I went to go check to make sure it was the right pages. So if you go to the book and type in A2, it'll give you the pages right here. It's the same thing. And then if you go to the next page, well, that was A3.
Okay, I guess I didn't understand what the value of A2 and A3 meant. And now I know that it's probably going to save my life in working these problems.
Right. Well, I'm glad you asked. Maybe I need to do this. Let me go back to the notes. Let me go back here and write and go purple. All right, just something like that. Or maybe say appendix pages. Yep. All we're doing is refining the notes. All right, so that's how we got the 0.1056. All right, so before we go any further with what that means, is everybody okay with just getting the value from the chart? Anybody? Yep, see that again. So once again, this last digit is always on this top row. Everything before that will be over here on this column. All right.
Okay.
All right. So now the next statement is very important. So the chart is always giving you less than. So if you go back to your chart, let me show you this in your chart. Notice how they give you this diagram right here. If you're talking about to the left of anything is always less than. Everything to the right is always greater than it. So let's look at just the generic number line. If I look at the number 0, everything to the right of 0 is always greater than it. Everything to the left of it is always less than it, right? That's always going to be the case. Left of is less than, to the right of will be greater than. That's always going to be the case no matter what numbers you're dealing with. If I look at the number 2, everything to the left of it is less than, everything to the right of 2 will be greater than. So your chart is telling you that it's giving you shaded to the left, whatever's to the left of. So just everything you pull from the chart will always be less than. So just remember that when we look at these keywords. So the chart is always, once again, the chart is always less than. Chart always gives you what's to the left of your Z-score.
I got a question.
Yes, sir.
How are you gonna send this to us, like on announcements?
I will send it to you in an email. It would be the same way. It would just be an attachment.
Gotcha. I get what you mean.
So I really wouldn't, I mean, this probably wouldn't affect how you guys see it. I wouldn't use SIS because I can't send a file through SIS. I would have to copy all of your emails, then put it in, then send it through my email stuff. So you would get it as an attachment though.
I get what you mean. Okay. Thank you.
Quick question.
Yep.
I know we have the book, but is there any way we can Google this?
Don't.
Okay.
Because all Z-score charts are not created equal, even though they'll give you the same value. Like some Z-score charts, they give you just a piece of it, and like there's a process, and it's not this process.
Okay.
So the chart I'm giving you, you're gonna have one process that you can lean on, and to me, it's easier to use. So I wouldn't Google them because unless you know what you're doing for sure, like what's different, the differences between. I think I've seen like 3 different types of Z-score charts.
I'll wait for your chart.
Yeah, so yeah, I'll try to get it to you tonight. So yeah, I try to do it before I lay my head down. And so there will always be a key phrase that will let us know what we should do with that chart value. And I'll show you, examples of those key phrases. All right. So shorter than, would be, another way of saying less than. Someone is shorter than you, then, their height is less than yours.
Hey.
And so since that represents less than, that means we would use the chart value. Remember, the chart value always gives you less than. So anything that, like I said, suggests less than. So if you're talking about temperature, colder, height is shorter. Somebody talking about weight, lighter, what else? What else? Below, could be another thing used. I should have a little chart at the end that, give you just examples of key phrases, but just give you an idea what we mean by key phrases that will let you know this less than. So once again, if you're talking about less than, you're going to use the chart value. So that's one of our scenarios. There are only 3 scenarios, so less than is one of them. So conclusion, the probability that a newborn seal would be shorter than 28 inches is going to be 10.56% or about 11%. So don't forget, we got that 10.56 from converting this to a decimal, to a percentage, moving your decimal 2 places to the right. So
2 places to the right. Okay. Gotta remember that.
all right, can I scroll up? So that's one scenario. Like I said, there are 2 more. So the next 2 scenarios, we're going to use the same situation. We're going to still be dealing with newborn seal pups. Going to have the same mean, same standard deviation, but it's going to be a different scenario. So the next one is, what is the probability that the newborn seal or newborn selected at random is longer than 32 inches? So before we're looking at shorter than, now we're looking at longer than. So what would we do if it was longer than? All right, scrolling up. Same process, convert that data value to a z-score. So we have 32 inches as our data value. Mean standard deviation the same as before, 29.5, 1.2. Plug them into your formula, 32 minus 29.5 divided by 1.2, and you get 2.08. Don't forget to round it to 2 decimal places. Round it to 2 decimal places. All right, so we hit the chart. Look for 2.0 on the left side, the left column, 0.08 on the top row. They will meet up at 0.9812.
Go to the chart.
All right, okay, we're scrolling up. So we have our chart value, 0.9812. Don't forget though, the chart value always represents what's to the left of or less than. We're looking at longer than this time, which represents greater than, or in other words, to the right of our data value. Am I okay with step one? Everybody done with step one? All right. So now everything, the amount of space under the curve is equal to 1. We talked about that before. Well, I thought we did. I might be thinking about another class. Anyway, it doesn't matter. We don't need to go to a whole nother section for that. Just know that everything under this curve is equal to 1. 50% of your data is to the right of your mean, 50% of your data is to the left of your mean. So if I want to know what's to the right of a data value, and I already know, let's go here, just a rough sketch. If I already know that this is 0.7 over here, and I want to know what's over here, subtract the 0.7 from 1, and that'll give me 0.3. So that will always be the case. You know what's to the left because the chart value will give you what's to the left. If you want to know what's to the right, you're going to subtract the chart value from 1. And so that's what we did. That's what we're saying here. To find what is to the right of, or what is greater than, you subtract the chart value from 1. Oh, I wrote that right there. Everything under the curve is equal to 1. So that's what I was just saying. All right, and scroll up. All right, so to find longer than, we just said we would take the chart value, subtract it from 1, so that will give me 0.0188. So the probability that a newborn seal would be longer than 32 inches is 1.88%, or about 2%. All right, any problems before we look at the last scenario?
No. Hold on. Can you go back to the red
Yep,
to
yep,
find what is the right of
Right.
right? Thank you.
Not a problem. All right, let me know if I'm going too high. So that's all I want to start right there anyway. So the black one, last example in black, what is, at least I think it's the last example anyway. What is the probability that this randomly selected seal will be between 27 inches and 31 inches long? All right, can I scroll up to the green?
Yes.
Okay, cool. Give everybody get a chance to get caught up before I start explaining.
1 second.
Not a problem. Y'all know we got till 10 o'clock. We good.
9.
Oh, I was gonna say you're a lie. Stomach is grumbling.
Now, is it rumbling because you're hungry or I made you nervous when I said something about 10 o'clock? You got the
I think
BGs.
it's a combination of both.
Okay, I'm ready.
Okay, sounds good. Sounds good. So everybody up to that blue, up to the blue. Okay. So we want to look at the probability. This is our third scenario. Should be the last scenario, unless I did something extra down there. I don't know. But the first situation was less than or shorter than. The second situation was greater than, longer. And this situation is between the two values. So the first thing you want to do is find the z-score for both of your values individually. So the mean is going to be the same, standard deviation is the same, but we have two data values that we have to find the z-scores for. Excuse me. So 27 will be x1, 31 will be x2. And like I said, plug into the z-score formula, find your individual z-scores for each one of those. So I got z1 is going to be negative 2.08. Z2 is going to be 1.25.
Oh, so now I see. Okay. Be 1.2 equal to 1.25.
And second step, you go to the chart for both of them individually. So you should get two individual chart values. Got a question, man?
So pretty much we had already had 2.08 and 1.25 in the previous one.
When you say, oh, you're talking about because they were older values? What you mean?
Mm-hmm.
Oh, wow. I guess I just be writing down notes, man. So yeah, I know I remember 1.25. Yeah, so you're probably right. But I didn't treat it that way because I wanted to make sure we were doing the process. So,
Okay.
Yep. So yeah, if they were repeated values, you're probably right. But just want to make sure I emphasize the fact that this is the process you would go through, put them in the z-score formula, and then go to the chart. Yep. Everybody good? Any questions? Any questions?
Equals negative 2.8.
All right, didn't go all the way up yet. So are we done with step one?
I'm almost.
Okay. Not a problem. All right. So just to give you a visual as to why we're doing what we're about to do. So we're talking about the between the two values. You want the amount of data that's represented or the probability of getting between the two values. So we know the chart gives us what's to the left of the data value. So this is to the left of Z1. This amount is to the left of Z2. So if I were to take that purple and subtract it from the blue, I would be left with just the red part. So just putting a visual on it, but bottom line is we're just going to subtract the two chart values. Yep. So to find between, we will subtract the chart values. And notice what we're doing here, just like before, I subtracted the chart value from 1, and I'm subtracting the two chart values. We're not subtracting z-scores. We're using the chart values. I know people have done that by mistake in the past, subtract the z-scores or subtract the z-score from 1. It's the chart values that we are subtracting. So you use the z-score to get the chart value, then you do the calculation with the chart value. All right.
What is the chart value to? Is that 949 or 944?
All right, you're talking about right here? What you said?
No, it says Z2 equals 1.25 and then it's CV2 equals 0.
Oh, yeah.
8944.
8944. Uh-huh.
Oh,
Yeah.
okay.
Yeah. And then this value is the same one as this one down here, So yeah.
Okay, gotcha.
44. See if I can write that 4 better. It's so funny you mentioned that because when I first started teaching, I used to write my 4s like this. But people, y'all know my handwriting isn't the greatest. So then people would ask me, was it a Y? When I would get lazy with my writing. So then I went through the process of converting it to 4s. And now people ask me, are they my 9s? So it's just like, I'm like, I ain't going back. So it's just, y'all just got to deal with these 9s. So.
Gotcha.
Question.
Again.
When you get that second chart value, you subtracted 1 from the value you got it from the chart, right? To get that. Is that correct?
This value right here?
Yeah, you subtracted whatever the value from the chart was, subtracted from 1, got you that number. Is that correct?
No, we just we had 1.2 over here, 0.005 up here. And where
that came. Okay.
Yeah. Mm-hmm.
And when you subtract that from 1 to figure out.
We only do that if the keyword here is greater than.
Okay. All right.
That's the only time we subtract it from 1. Yeah. But each one of these chart values, and that's a great question, each one of these chart values, you always do it this way. That's the only way you can get the chart values. Then from there, the keywords or the key phrasing will let you know if you do anything else with that chart value. All right. Oh, that was just me reminding, do not subtract z-scores. No, we do all the work with the chart values. So to find between, we went ahead and subtract the two chart values, 8.99, let me get it right, 0.8944 minus 0.0188. That gives us 0.8756. The probability that a newborn seal will be between 27 and 31 is 87.56% or about 88%. All right, are we good? Are we good? All right, so here's the summary of our 3 scenarios. So we have, like I said, just 3 scenarios. Yes.
Back up to the red for a second, please. I'm sorry.
No, you don't have to apologize. Yeah, right there, see if some of that in there.
Yeah, I'm all set.
All right. All right. So just summarizing our 3 scenarios and what you would do if you come across it. So if it's less than, you use the chart value. Whatever value you get from the chart, that's the value you use. If it's greater than, you subtract the chart value from 1. And then if it's between, you're going to subtract the 2 chart values.
I do have another question.
Yes, sir.
You subtracting the chart values, are you subtracting, it's always the chart value 2 minus chart value 1, or is it chart value 1 minus chart value 2?
Well, I'll say it like this, depending on how you decide to label them, it may be different, but it's always the greater one minus the smaller one.
Okay.
Yeah, because you don't want your chart, you don't want your answer to be negative. You shouldn't have a negative percentage.
Yeah, that's what I was asking. Okay.
Yep. All right, is everybody good? And then here's what I was talking about before, just giving examples of keywords or phrases that will dictate less than, greater than, or between. So less than, shorter, below, colder, under, beneath, things like that would suggest less than. Greater than, longer, taller, above, hotter, things like that would suggest greater than, and between is just between. I couldn't think of anything other than between. Yep, those are your 3 scenarios, and then your keywords that could suggest your scenarios, depending on the application.
What's the word under below?
Colder.
Okay, thank you.
I got percentiles down here. Was that at the end of that section? Let me see. Okay, they do talk about it. Okay. All right. So if I don't this chart, scroll up. Anybody? Just want to see how far this goes. Yep, I thought so. All right. So it's the last thing. They have percentiles at the end of this section. And then we'll be done with it. Is everybody good on this chart? All right. All right. So percentiles, the kth, that's K and then TH, like fifth, kth percentile of a set of data is a value such that K% of the observations are less than or equal to the value. So you run into percentiles. A lot of times we talk about your kids, take your kids to the doctor, and they say that their height is in the 70th percentile, or their head is in the 30th percentile, something like that. We talk about
You have
measurements.
small kids, don't you?
Huh? No,
You have small
I
kids.
do, but my son, it's so funny you say that. I used to use the example, but I stopped because I keep joking on my son, but it was funny. His head was in the 90th percentile. So that means only 90% of the kids in the United States had a head smaller than his. And so I used to call him head because of that for a little while, but he grew into it. He good now. So so I said, let me stop using that. Like for a long time, I would use that example, but I said, let me stop using that example talking about my kids. But that's why you have them, so you can talk about it, right? So it's all good. So yep. So we have here just an example of how that works. Jennifer just received the results of her SAT exam. Her SAT math score was 600 and is in the 74th percentile. So what does that mean? And going back to that 90 percentile of his head, like the rest of his body was nowhere near 90%. So I'm just like, I can't even say you're gonna be a legit athlete, like, where your height and your body, like, come on, man, give me something. Give me something to work with. Yeah. So if Jennifer scores in the 74th percentile, that means 74% of the people who took the exam scored 600 or less. And then 26% scored better. And that's just taking that 74, subtracting it from 100. And yep, so that's all I put in there for that. I didn't see, if I remember correctly, the reason why I didn't do anything else outside of that, I didn't see anything that calculated using percentiles. If you see something that, that's extra, just feel free to, bring it to class and we can talk about it. Not a big deal. I don't remember seeing a problem that actually made you do anything more than that in the homework. So that is it for chapter 6. That's it for chapter 6. So next class, the floor will be open. I'll open up the floor for questions first. Anything that you guys have, anything you want to talk about, and didn't feel like, come to the office hours or didn't have time to come to the office hours, or set up a time outside of class. You can bring them to class and we will address those issues first and figure out where we're gonna go from there. All right. Anything, anybody?
How many problems are you allowed to bring?
Ain't no limit. Do what you do. Yep.
Because chapter 5.
Okay, it's not a problem. Just bring them. And all I ask is that you actually bring them and don't just be like, man, chapter 5. You know what I mean?
No.
What you want me to do with chapter 5? So yeah, if you bring your problems, then then yeah, whatever it is, whatever you bring, and we'll go over. Yep, no limit. Now if it takes us past 9 o'clock, I guess that would be the limit. But so no limit on the problems you guys can bring. All right. Anything else? Anybody else? Everybody good?
I have a quick question.
Yep.
Under the notation, I just didn't know what that word was under lowercase.
Okay, hold on a second.
Under the Greek letters.
Yep, I'm about to scroll right up. I just want to make sure. Is everybody good? Can I scroll up? See somebody still copying. Oh, see a head shaking. Okay. I know it has something to do with sigma.
It was like the beginning of the 6.2.
Yep, sigma.
Okay, sigma.
Yep, Greek letter. That's the Greek letter, sigma, lowercase sigma.
Oh, I thought it was a Q. Okay.
Y'all just love taking shots at my hand right now. I just, yes, that's all right. That's all right. You're right. I did write it as a Q.
You're fine, but thank you.
Yep, no problem. Anybody else?
Yeah, I got something.
Yes.
You did post last lecture because that's when I was feeling sick.
Yeah,
Okay.
it should have went out.
Okay.
Everybody, did y'all get
Yeah.
it? Okay,
Yeah.
okay. Just want to
Okay.
make sure because I'm human. I could forget, So it's
Yeah,
all good.
I got COVID.
Oh man, you
Yeah,
doing all
man.
right?
I'm feeling fine. I had fever that day, but I was really bad that day. But I'm fine now. Still got a cough, but
Gotcha.
now I'm
So,
Glad you're
quarantined.
doing better, Corey.
yeah,
Thank you.
yeah. Most
Didn't hit me
definitely.
that bad. I just had the fever was the worst part of the coughing.
Mm.
Gotcha.
I'm good now. Thank you for asking.
Definitely glad you're feeling better.
Yeah,
Thank you.
for sure.
And I was vaccinated too. I still got it.
Yeah.
Don't tell me that scares me.
I'm not gonna tell y'all about my third experience, my booster then.
What you caught you caught COVID 3 times?
No, I got the booster on September 23rd.
Oh.
Got mine scheduled next in a couple weeks. So
okay.
I have been scared because the second shot kicked my butt. I was down. I had like 103 fever. I had the chills, like all of that my second shot. So I've been so scared of my booster because I'm like, it's definitely gonna kick my butt more. I feel
Oh man. Well, we most definitely hope it doesn't. I drank a lot of water. I don't know. I was good. I don't know.
No, my third one, I had the swollen lymph nodes, everything.
Wow.
Yeah.
Y'all got me scared to get my booster.
Right. I'm like, well, do I need the booster? Do I really need it? Oh man. Well, thank you for dropping fear into our hearts as we close out the class.
my bad.
Well, I'm a nurse, so I got the booster. So.
Oh, okay. Vaccine just makes it less severe. It doesn't, like the flu shot. Yeah, it doesn't stop you from getting it, just make it less severe. Yeah. So anything else? Anybody else want to tell us about how bad and how violent our neighborhoods are before we close out? I'm just messing.
Oh God, this is a hot topic right now.
Yeah. So before we go anywhere else with this conversation, I'm gonna go ahead and close it out.
It's probably for the best.
Right. So you guys have a good one. Be safe. And I'll look for that email with the Z-score chart. And I will see you next class.
Okay, thank you.
Thank you. Everybody be safe.
All right, take care.
You
Be
too.
safe.
Thank you.
All right.
Professor, did you want to stay back and look at,
Oh,
try to look at that, or?
Yeah, we can.
Okay.
I'll give you the ability to share your screen in a second. Hold on. Matter of fact, let me stop the recording since we don't need this.